The universe is cool. That's why. Yeah, light speed is a convention. So it gets even stranger. What have we said so far? We've talked about time dilation. We've said that if one object is moving relative to another object, the moving object experiences time slower. We talked about length contraction. We said if one object is moving relative to another object, the moving object's lengths contract in the direction of motion. We also said that explains why it's impossible to measure how far stars are from us or planets are from us. We always are assuming we're measuring with Earth at rest. But as soon as you start to do the journey, especially if you're going near the speed of light, space-time itself will compress in front of you and you will travel a shorter distance than we measured from Earth. Third thing, Einstein showed us that as objects speed up, there is an increase in mass. It's governed by the equation m equals m0. You know what? It can be written using the Lorentz factor, m equals m0 over gamma. And I think I've also put that version on your green sheet, where m0 is the original mass at speed 0. And so you can decide which way you want to memorize that, Pinnell, whether you want to treat it as MO, original mass, or M0, mass at speed 0, the resting mass, often called the inertial mass. And M is what we call the spelling that wrong, Mr. Duick, relativistic mass. As you speed up, the relativistic mass increases. And this is why in the last unit when I said we're going to treat inertia as though it's mass, even though they're not technically the same thing, F equals ma only works when you're not going near the speed of light. But as soon as you start to go near the speed of light, that m is changing, and now something different from inertia is going on. So, suppose an object had a mass of 10 kilograms at rest. What would its mass be if it was traveling at a speed of 2.5 times 10 to the 8th meters per second? Is this asking me to find m or m0? What's m0? More specific in this question. 10. So it's asking us to find m, which is m0 over that square root thingy. So it's going to be 10 divided by big square root of 1 minus, this time so we'll have to put in the numbers. On the top is going to be 2.5 times 10 to the 8th. On the bottom is going to be 3 times 10 to the 8th. You saw in the video it's actually 2.997, close enough to 3 that we don't quibble over that. Don't forget the squared. Let's get out our trusty calculators. How would I type this in? I'd probably do the brackets first. I'd probably go 2.5 scientific notation button 8 divided by 3 scientific notation button 8. And I would get 0.833333 repeating. Then I would square that. I'd get 0.69444 repeating. Then I would go 1 minus that. I get 0.30555. Then I would square root that. And then 10 divided by that. This 10 kilogram mass, if it was traveling at 2.5 times 10 to the 8th, pretty fast, would have a mass of 18.1 kilograms. It would behave as though it would have that mass.
Stops moving.
Yep.
Right after that state.
Nope. As it slows down, it would lose mass. So, by the way, what that means is whenever we're giving you a mass of an object, we're always implying or assuming at rest. Okay? What was your question?
So if you go into the speed of light, you're going to time slower.
Can you hold that question for about 5 minutes and then ask it again? Let's go 98% of the speed of light. So that's going to be m equals, let's see if we can just plug it in, 10 all over the square root of 1 minus 0.98 c over c all squared. Ethan, do you see? Do you see? Do you see? What do you see? That's kind of nice. This one I can probably try typing in one fell swoop. It's going to be 10 divided by square root bracket, or you'll use your fancy schmancy fraction button, 1 minus 0.98 squared. So at 98% of the speed of light, it now has a mass of 50.3 kilograms. What about 99% of the speed of light? You know, if you typed this in one line on your calculator, you might be able to backspace and edit and just change the 98 to the 0.98 to a 0.99. And this is me also saying it's worth reading your manual and figuring out how to bring back the previous line, because that's, you may have noticed, way handy sometimes in the homework. 70.9 kilograms? I need to change this number because they've upgraded the Large Hadron Collider, but when I first typed this, the fastest the Large Hadron Collider could get protons was 0.99, that. 1, 2, 3, 4, 5, 6, 7, 8 nines followed by a 1. So I'm going to try typing that in. 1, 2, 3, 4, 5, 6, 7, 8 nines followed by a 1. Don't forget the squared. Close off the bracket. What would this 10 kilogram mass now be?
71.
No, it's going to be way bigger than 71. How about 500 kilograms? $74,500 kilograms. 1, 2, 3, 4, 5, 6, 7, 8, and then a 1. Yeah. What if you go faster? So, to get to the speed of light, what would the mass hit as soon as you tried to reach the speed of light? No, not 0. Infinity. So answering your question, you asked if we could go faster than light. So first of all, to go faster than light, you would need to move an infinite mass. Do you know how much energy it takes to move an infinite mass? More energy than there is in the universe. Conclusion, we can't, any object with mass cannot go light speed, or let alone faster than light. It can't even get to light speed. Protons don't have much mass. To get the protons to go this fast here takes enough energy to power a small town. And that's a proton. Not a big thing. So if you want to get a spaceship, you know, that has a mass of several million tons to go that fast? No. So anyways, the answer here was, what was it, Mr. Dewick? 74,535. Oh, 36. Round off properly, Mr. Dewick. Why is Albert Einstein so respected? I already told you he kind of came out of nowhere because he wasn't even working in a university. He wasn't technically a physicist. He was working in a patent office, but he was thinking a lot about light. Put your pencils down, look up.
That's your takeaway from the video. Thank you.
What's your homework? 2 things. I'm going to give you a take-home quiz in just a second. The take-home quiz is on the first lesson, which was relative speed. 2 objects moving at different speeds, 2 trains moving at different speeds, a police car trying to catch the bad guys, and it's got time dilation on it. So it does not yet have length and mass. But for now, number 1 is good. Oh, heck. You know what? Yeah, all of them. Okay. It's not too many, actually. And I attached the answers, and I said there's an answer key showing all my steps at pitmath.com. I'll print an answer key showing all my steps. I printed 2 answer keys for the time dilation assignment. They both walked off. If you accidentally borrowed it, just put it back on the steel table there.